Hello everyone. Today we're going to be discussing celestial navigation. A few weeks ago, a friend and fellow YouTuber, MCToon, put out a celestial navigation challenge. He gave observations of the angles to 3 stars at a given time and asked viewers whether they could determine his location on Earth. This video is a mathematician's way of trying to solve the problem. Suppose the star has a ground position given by a latitude and longitude. If this is the Earth, the ground position is the point on the Earth's surface in a direct line between the star and the centre of the Earth. We take the Earth to have unit radius. Then the GP, ground position, corresponds to a vector n, say, with n squared equal to 1. So that is the vector n. Suppose we have 3 stars. There are ground positions n1, n2 and n3. If that vector is n, and we're at the location x, that angle alpha is the angle measured between the star and the horizon. It follows that that angle is also alpha. So x dot n is equal to sine alpha. That is, we know that x lies on a plane given by this formula. Well, this holds when n is any one of n1, n2 and n3. So in particular, x cross n1 cross n2 is x dot n2 n1 minus x dot n1 n2, and that's equal to sine alpha 2 n1 minus sine alpha 1 n2. Cross this with n3, sine alpha 2 n3 cross n1 minus sine alpha 1 n3 cross n2. From the triple vector product identity, you end up with n3 n1 n2 times x minus n3 dot x n1 cross n2 is equal to sine alpha 2 n3 cross n1 plus sine alpha 1 n2 cross n3. Or in other words, x is 1 over n1, n2, n3. That's the triple scalar product of, well, that thing is sine alpha 3 n1 cross n2 plus sine alpha 2 n3 cross n1 plus sine alpha 1 n2 cross n3. And it's pretty simple to see that x dot n1, for instance, is 1 over n1, n2, n3 times sine alpha 3 n1 dot n1 cross n2, which vanishes, plus sine alpha 2 n1 dot n3 cross n1 vanishes, plus sine alpha 1 n1 dot n2 cross n3. And that thing cancels off with a triple scalar product, just gives sine alpha 1. Similarly with n1 replaced by n2 and n3 and alpha 1 replaced by alpha 2 and alpha 3. So this point lies on the intersection of the 3 planes and therefore is the location of the observer. Note that n1, n2 and n3 is not 0 if n1, n2 and n3 are linearly independent. This is the generic situation. Now, it is very unlikely that the location we have just determined lies on the surface of the sphere. That is because there will be inherent errors in alpha 1, alpha 2, and alpha 3. So now let's make the replacements. Alpha 1 goes to alpha 1 plus epsilon, alpha 2 goes to alpha 2 plus epsilon, and alpha 3 goes to alpha 3 plus epsilon. We introduce epsilon to correct for any systematic errors such as refraction when measuring the angles to the stars. We can fine-tune epsilon to make sure that our final answer has the property that mod x is equal to 1. That is, the point lies on the surface of the Earth. In this case, we have x is equal to A times cos epsilon plus B times sine epsilon, where A is the triple scalar product, the denominator, times sine alpha 1 n2 cross n3 plus sine alpha 2 n3 cross n1 plus sine alpha 3 n1 cross n2, and B is 1 over this triple scalar product cos alpha 1 n2 cross n3 plus cos alpha 2 n3 cross n1 plus cos alpha 3 n1 cross n2. This follows from the addition formula. Sine alpha plus epsilon is sine alpha times cos epsilon plus cos alpha sine epsilon. So what value of epsilon do we need to take to make sure that x lies on the unit sphere? Well, x squared is a squared cos squared epsilon plus 2a dot b cos epsilon sine epsilon plus b squared sine squared epsilon. We want that to be equal to 1. Well, let t be tan epsilon, then we get sec squared epsilon is equal to 1 plus t squared is equal to a squared plus 2a dot b t plus t squared b squared. Or in other words, t squared into b squared minus 1 plus 2a dot b t plus a squared minus 1 is 0. And therefore t is equal to plus or minus the square root of a dot b all squared minus b squared minus 1 a squared minus 1 minus a dot b all divided by b squared minus 1. And we'll take the plus or minus sign to be the same as that of a dot b. That would mean that t should be small. Then x is equal to 1 over root 1 plus t squared into a plus tb, and that will be the location of the observer. Let us apply what we have just derived for the particular problem that MCToon has set. He gave the following data. Polaris, which has right ascension of 44.50015 degrees, a declination of 89.36 degrees. It was measured with a value for alpha of 45.6 degrees. Procyon has right ascension of 115.1144 degrees, a declination of 5.17 degrees, and alpha is 25.2 degrees. Arcturus, right ascension 214.17 degrees, 19.06 for the declination, and 45.7 degrees was the measured angle. The time of each of these in universal coordinated time, that's GMT, was 5:21:45, 5:19:51, and 5:22:33. These times occurred on the 28th of March 2022. Next, we need to know that the March equinox occurred on the 20th of March 2022 at 15:33 and 30 seconds, and the solar noon on the Greenwich meridian occurred at 12:07 and 58 seconds. Let omega be 2 pi over d, where d is 1 day, and omega primed will take to be 2 pi over d primed, where d primed is 23 hours, 56 minutes, 4.1 seconds, which is 1 sidereal day. Next, we want to work out the longitude of the subsolar point at the equinox. Let's call this phi naught. It is given by phi naught is minus TEQ minus T noon times omega. That's equal to minus 51.133 degrees. So this determines the angle from the Greenwich meridian from where the subsolar point occurred on the March equinox. Now we wish to work out the ground position of the stars. The latitude is pi over 2 minus theta, where theta is the standard spherical polar angle. This is also equal to the declination of the star. To work out the longitude phi, we take phi naught and add the right ascension value to it, that would give us the longitude at the moment of the equinox. But since we're not at the equinox, we also have to subtract t minus TEQ times omega primed, which accounts for the amount of rotation the Earth has experienced between the time of observation and the equinox. For Polaris, this gives phi as 138.587 degrees. For the other stars, we get minus 150.322 degrees and minus 51.9432 degrees. Next, construct the vectors n1, n2, n3 using the n is sine theta cos phi, sine theta sine phi, cos theta, our standard spherical polar coordinate expression. From this, we can apply the formula that we derived earlier on, and we find that the location of the observer has a latitude of 46.7124 degrees and a longitude of minus 93.2742 degrees. Let x0 be the true location of the observer. Now MCToon has kindly given me the true longitude and latitude of the observer. And from this we can work out the distance between x and x0, our estimate and the true location. And when converted into a distance on the surface of the Earth, it turns out to be 6.75 miles. So our calculation has provided a rather satisfactory estimate for the location of MCToon when he took these measurements, given the data he provided. And that concludes our little investigation into celestial navigation.